Welcome to Chapter 2. It's a new chapter, so I felt like I should be in the middle of your screen for some reason. Chapter 1, all the matrices that we encountered there were the results of a system of linear equations. In Chapter 2, we're going to start looking at the matrix as an object in its own right, not necessarily just shorthand for a system of linear equations. But we'll just look at things that all matrices share in common and what we can do with them on a theoretical level. We're going to start with just some basic matrix operations. How do you add matrices, how do you multiply matrices, that sort of thing. So 2.1 lays the groundwork, and we will move forward from there. Okay, so let's talk a little bit about some of these basic matrix operations. I'm going to move myself into the corner where I belong, and let's just talk about a couple basic ideas. So we should know how to add and subtract. And the short story there is it's just individual entries get added. So let's see, you've got 1, 2, 3, 4 plus 5, 6, 7, 8. The results there are still going to be a 2 by 2 matrix, and you add the upper left. So 1 and 5 becomes 6, and you add the upper right. So you add the matching entries all the way across. So that'd be 8, 10, and 12. This does mean that not all matrices can be added, right? They have to have matching dimensions. So you should be able to add and subtract. Subtraction is the same, obviously, just subtract. You should be able to do scalar multiplication. And keep in mind, scalar just means an individual number, what we used to call a constant, but not a matrix or a vector or anything. So you should be able to do 2 times a matrix. I'm doing 2 by 2 matrices here because I'm lazy, but this works for any size. You can always multiply a matrix by a constant, and this does mean multiply every entry inside the matrix. So this will become 2, 4, 6, 8. And any good matrix calculator will be able to do these things. If you want to do 2 times a matrix, it should be able to punch that out pretty quickly. It is important, of course, for us to know how these things work, because pretty soon we'll have things like h's and k's and variables, other matrices even in the individual spots. So we'll need to know how the algorithm works. But okay, so those are fine, and along with those we kind of get our first theorem. Let's see, let's get rid of that. Get our first theorem. And this is kind of a lot of the properties that you would expect. So A, B, and C are matrices that are the same size. R and S are scalars. So you get things like matrix addition is commutative, and it's associative. And if you add the 0 matrix, right, there still has to be a matrix of the right size. So when they say 0 here, they mean, like if A is 2 by 3, this is a 2 by 3 matrix as well. It's all zeros. But anyway, adding a bunch of zeros to a matrix still produces the same matrix. Scalar multiplication distributes, and the matrix distributes to scalar addition here, and if scalars are multiplied, it's associative. Okay, so some of the basic things you would expect to work still work. The reason why they're making a big deal out of this is there's a couple of the basic things that you might expect to still work that don't. So we'll get to those in a minute. But for the moment, all of these things still essentially work the way that we want them to work. Okay, so let's talk about matrix multiplication. Let's see. So matrix multiplication. So that means rather than multiplying by a scalar or multiplying by another matrix. And granted, we already know how to do certain types of matrix multiplication. Namely, we know how to multiply a matrix by a vector. I'm just making this up. There's nothing magic about these particular numbers. But we know how this works, right? The vector sort of says do 4 of the first column and 0 of the second column and 2 of the third column and add them all up, right? So it says 4 times 2, 1, plus 0 times 3, 4, plus 2 times 1, 6. And you can crunch that out, and I'm not even going to finish because you know how to do that. And you can multiply our matrix by any vector as long as it's a 3 by 1 vector, as long as it's the right size, right? So again, that means exactly the same thing, just different scalars outside of each of these individual vectors. Actually, that's be minus 1 and plus 5. Okay, I lied. I am going to finish these. I can't stand it. Okay, so let's see. This is going to be the tops. I'll just do the top entries first. This will be 8 plus 0 plus 2 is 10. And the bottoms will be 4 and 12, so 16. And on this one, the tops will be 4, 7, and 5 is 12. And 2, oh, minus. Sorry, I forgot this was a minus. 4 minus 3 is 1, plus 5 is 9. Okay, on the bottom, 2 minus 4 is negative 2, plus 30 be 28. Okay, so that's fine if we want to multiply a matrix by a vector, as long as the dimensions are right? As long as if there's 3 columns, you have 3 entries here. What we haven't yet done is multiply a matrix by another sort of full-fledged matrix, not just a single column. So 4, 0, 2, 2, negative 1, 5. So there it is, something we don't know how to do yet, theoretically, is multiply a matrix by another matrix that's not just a vector. And guess what? You do know how to do this already. You're smarter than you thought. Guess what this answer is? It turns out it's 10, 16, 9, 28. So it is just the results of doing the first column and the results of doing the second column. So really, when you look at this matrix A times another matrix B, you really want to look at the matrix B as its own little set of vectors, and then just do the first vector, do 4, 0, 2 times the matrix, that becomes your first column in the answer, and then do your second vector, do 2, negative 1, 5, and that becomes your second column in the answer over here. Okay, so fine, it's just essentially a way to say repeated vector multiplication when you do matrix multiplication. So this is one way to think of doing matrix multiplication. You'll definitely want to have that in your tool bag. You'll also want to have a second way to do the exact same matrix multiplication. So let me clear out some of what I've got here and just show the second way. Let's see, I'm going to keep the bottom so we know what answer we're heading for, but you'll want to have this second technique in your tool bag as well. So it's just another way to keep track of where all the numbers are. But you can compute, like say, let's just figure out the 10 first. Let's just figure out the top left entry. So you'd say this entry, this 10, is the, where is it in the matrix, in the answer matrix? What we're trying to figure out is the first row, first column spot. And that means you should take the first row and match it with the first column. Oh, I see I'm not doing the full problem here. Hold on. I'm trying to do the same problem, so let's get the second column on here. Let's get the 2, -1, 5. Okay, now we're doing the same problem. But the process doesn't change here. I'm still trying to figure out the 10, so basically the first row, first column slot in the answer, which means take the first row and multiply it by the first column. So what I mean by that is it's 2 times 4, which is 8, plus 3 times 0, which is 0, so we're still at 8, plus 1 times 2, which is 2. So total 8 plus 2, 10. And let's say we want to figure out this slot right here, which we happen to know is going to be 16. But we'd say that slot is the second row, first column spot, right? It's in the second row, first column. So we should look at matching up the second row and the first column and multiply those. So multiply entries. So 1 times 4 is 4. 4 times 0 is 0. 4 plus 0 is still 4. 6 times 2 is 12. So 4 plus 12, 16. Maybe I'll write this out actually, just to make it clear as we figure out the 9 spot. So the 9 is in the first row, second column. So first row, second column. And what I need in there is 2 times 2 plus 3 times -1. Plus 1 times 5. That's 4 minus 3, which is 1, plus 5. 1 plus 5 is only 6. What did I do wrong? Let's see. I'm doing first row, second column, 4 minus 3 is 1. Plus 5 is 9. Did I do something wrong on the first one? Boy, the internet trolls are going to have a heyday with this. Let me check my okay, 4 minus 3 is 1. Plus 5 is 6 is what I'm trying to write up here. 6. Okay, now let's check the 9 down here. The 9 was the result of... Oh yeah, that went away. But it should have been the results of... 2 times 2, 1, minus 3, 4, plus 5 times 1, 6. Let's double check all that. That would be 4, 2, minus 3, 4, plus 5, 30. Let's see, so 4 minus 3 is 1, plus 5 is indeed 6. Okay, so my 9 was wrong. And let's check the other one. 2 minus 4, -2 is 36. I clearly cannot be trusted with a pen tonight. Okay, that's 5 times 6 is 30. 2 minus 4 is -2, plus 30 is 28. Okay. So I should have a 6 there. Yikes. Okay. So if I was finishing my alternate form of matrix multiplication, it's a good thing I'm doing this both ways to catch my mistakes. It'd be 2 minus 4, so negative 2, plus 30, 28. Really, you're doing the same arithmetic operations, you're just doing them in slightly different order. Obviously this video is an excellent demonstration of why you don't want to do this by hand for the most part. You definitely want to understand the process, and you definitely will make mistakes if you do it all by hand. So please make use of a matrix calculator once you understand the process. Okay, so let's, if I am brave enough, let's go a little bit further and make one more point before we finish this video off and jump on to the next one. So I'd just like to point out, let me multiply a couple matrices here, and again I'm just sort of making these up off the top of my head. You can use either one of the two methods that we just talked about to multiply these two together. I think I'm going to do the second method. So first row by first column become negative 2 plus 2, so 0 right there. First row second column would be 1 times 3 is 3, plus 10 is 13. Second row first column, so negative 6 plus 4, negative 2, and 9 plus 20, 29 in that spot. I really hope I did that right, but let me know if I did it wrong. I'm sure you will. Hopefully the concept at least is clear, is that we just multiply two matrices together and we got a matrix result. So let me just multiply these two matrices together in the other order. Okay, so let's do the first row by the first column to get the first row first column spot. So that'd be negative 2 plus 9 would be 7. And notice, not only is like our entries in different places, they're just totally different. Like there was no 7 in the first multiplication, and we've gotten a 7 in the second one. This is not me making a mistake, again, I hope. But in general, matrix multiplication is not commutative. A times B as matrices generally does not equal B times A. So that's worth noting. This is really the first time in your mathematical career you've gotten multiplication that's not commutative. Won't be the last time if you keep going, but it's their first time. So I'm not even going to finish this multiplication out. You can finish this out, but the point I wanted to make here was just that matrix multiplication is non-commutative compared to matrix addition and subtraction, which are commutative. Not subtraction, just addition. I clearly need to end this video, so I'm going to chop it off right here, and I will see you in the next video.